Okay, so everybody good so far? Okay. Does it feel like a lot of stuff? It's weird because it's only one chapter pretty much with one extra section on the end of it. The first test was like 3 chapters, but this was definitely a long chapter. After chapter 4, the chapters keep getting shorter. So it's like you go longer, longer, longer. Now they get shorter and shorter and shorter. By the end of the semester, it will be whizzing by. We'll be done with chapter 7, which is as far as we're going. So it's really nice. Okay, so I'm going to go to the review sheet here. I may not go in perfect order of the problems, but I'm going to go somewhat in order. And again, throw out questions as you have them while we're going through this. This is a great time to ask questions, and I'm in no hurry whatsoever. So I'll take as much time as we need to get this cleared up. Okay, so here's the first question. Let's let A be the matrix 1, 2, 0, negative 2, 3. And then negative 4, negative 8, 0, 8, negative 12. Okay? And the first question is find a spanning set. Find a spanning set for the null space of A. Find a spanning set for the null space of A. Okay. Can anybody remind me how do I find the null space of a matrix?
0.
Okay, we augment the matrix with zeros. I'm just going to do it this way if you don't mind. I'm just going to simplify my writing. So the matrix A augmented with zeros, and then what do I do? EROs, exactly. I row reduce it to row echelon form. And on this exam, compared to the first exam, I'm going to be a lot less fussy about your ERO notations. You can do things relatively quickly. In this case, the first row is already okay, right? So I just recopy it. I'm not going to change that at all. First row is good. And what do I do in terms of for the second row? Take the first row times 4, add it to the second row, and notice what happens. It all zeroes out, right? Okay, oops, and I forgot I'm augmenting this with a column of zeros. I need to make sure I include that as well. There's a column of zeros there. Okay, if it helps you, notice in the problem I didn't have any variables mentioned, but you're more than welcome to imagine that there are variables attached to these columns, and you can of course use whatever letters you want. I'll just use X, Y, Z, U, and V. Okay, and so we have the row echelon form of the matrix. So what do we do next?
I like to write that in equations, but you can bust out the variables.
Let me write down the equations, because I'm not ready to bust out the variables actually. So I need to write down the equations. So this would be x plus 2y minus 2u plus 3v equals 0. And we just have that one equation. That's all there is. Okay? So that's good. It's never a bad thing to go back and write down what the equation is. And this is my pivoted variable, which is x. Okay? So what do I need to do next? Okay, so v is a free variable, so we could call it t. All right, good. What about u?
Whatever you want it to be. S.
Okay, it's s. All right, good. And then we're actually missing z. So does that mean that z is 0, by the way? If I have a column of zeros here?
No.
Not at all, right? The fact that the z doesn't show up in the equation means quite the opposite. It means that z is free. It can be any number you want. It's not going to affect whether this is true or not. So z is also free, so let's call it r. And then working backwards even further, y is also free. So I need another free variable. Maybe I'll use q, going backwards in the alphabet here. Okay, and so then finally we get to x. Is x free? No. So I have to take x and basically write it in terms of those other variables. So I'm going to get, if I move everything to the other side of this boxed equation, I'll get negative 2q, and then I'll get positive 2s, and then a negative 3t. That look all right? Yeah, Ken? No, x is not free. X is not free. These are the free ones here. X is the one that has the pivot on it. That means it's not free. Exactly. So X is not free. So this is what we end up with. So what you would want to do, what you could do, is you could write down what is the null space of A now. The null space of A, remember it's a subspace of R5, 2 by 5 matrix, it's a subspace of R5. So it's going to be a set that has 5 slots in it here. So negative 2Q plus 2S minus 3T, comma, Q, comma, R, comma, S, comma, T. Just write all that down. And then such that Q, R, S, and T are elements of the real numbers. So this is what the null space of the matrix is in this problem. Now that is not what the question is asking you for. The question says, find a spanning set for the null space of A. However, the first thing that you should do when you're asked for a spanning set of the null space of A is do this. Just find out what is the null space of A. Before you can find a spanning set for something, you have to know what the space is that you're looking at. So that's what we've done here, and this is actually most of the work. Okay, so this is what we've done. Are there any questions so far on how I got my null space here? Yes?
When we specify that the variables are free, do we have to reassign them to another?
Oh, good point. Do I have to relabel Y, Z, U, and V as Q, R, S, T? You actually don't have to do that. You could just say, look, Y, Z, U, and V are free, and X can be expressed in terms of those letters. I like to do the changeover to new variables just because it reminds me on every problem that I'm introducing free variables here. I tend to think of this part of the alphabet as free variables, and it just keeps me from getting confused about other things that are going on in this chapter. But you don't absolutely have to do that. This is a really good question. Okay, so here's my null space. So how do I get a spanning set for it? Now we bust out the variables. That's exactly right. So we bust out the variables. Pretty sure there'll be some busting out of variables going on Wednesday. So if we do that, what we can do is we can say, well, there's a Q. That's one of my variables. And then I just look at where the Q's occur. Well, I have negative 2 of the Q's in the first slot. And then I have 1 Q in the second slot, and nowhere else do I have a Q. So 3 more zeros after that. Okay? And then plus R is the next variable, and R would be multiplied by what vector here?
0, 0, 1.
There we go. 0, 0, 1, 0, 0. Very good. Okay, and then my next variable is S. So what's the vector that multiplies with S? 2, 0, 0, 1, 0. And the last one is T. And what is T multiplied by? Good. Okay. That expression right there is not the spanning set. That is a linear combination of vectors. So remember, when you're getting ready to write down your spanning set, you need to get these squiggly braces out and then just list, you're just going to list these vectors. You're just going to list these vectors. Okay, so negative 2, 1, 0, 0, 0, comma, 0, 0, 1, 0, 0, comma, 2, 0, 0, 1, 0, comma, negative 3, 0, 0, 0, 1. You just make that as a set. That would be the answer. Okay, everybody comfortable with that? This is a good question. This right here is what we always talk about when we're talking about linear combinations. A linear combination is where you have, scalars times vectors plus scalars times vectors plus scalars. Basically, whenever you see me write something that looks like this format, right, where you have constants times vectors added together, that's exactly what we have up here. We have scalars times vectors plus scalars times vectors, but because there's plus signs and so on in the expression, that's not your spanning set. This right here is your spanning set. Yeah, Pam?
Would you at any time just ask for the linear combination, or would you always go the step further to the spanning
I wouldn't be able to ask, I wouldn't know how to ask that question that would ask you to just write this down. Yeah, I'm gonna always be more interested in the spanning set. Yeah, that's a good point. Yeah, this one?
When you write down that answer, do you have to say like, list the vectors and say this spans R5? Or is that?
You can just say spanning set. If I've said find a spanning set for the null space, I'll know that you're finding a spanning set for what I'm looking for. By the way, this is not a spanning set for R5. This is a spanning set for the null space of A. Look at the question, right? This is a spanning set for the null space of A. R5 could never be spanned by only 4 vectors. That's one of our results. We know that the dimension of R5 is 5, and so if I only give you 4 vectors, they could not possibly span that space. They form a subspace of R5, and we know that the null space of a 2 by 5 matrix is a subspace of R5, but we don't want to say that it spans all of R5. Yeah, it's a good point. Would these, I'm going to take it a step further, it's a spanning set. Would these guys be a basis for the null space of A? This is just, let's call this a follow-up. Follow-up question. This is not on the handout, but I'm going to follow it up. Is this set a basis for the null space of A? Okay, right. We know that in order to be a basis, the vectors have to be both a spanning set and Li. So they're halfway. We know they're a spanning set for the null space. The question would then be, are they Li? Let's think about how we would test for Li. To test for Li, I would take these 4 vectors, and I would write them in a linear combination. Well, I actually already did that up above. I didn't use C1, C2, C3, C4, but look what I have right above here. I have a linear combination of the 4 vectors. And what would you set, if you're testing for Li, what do you set that linear combination of vectors equal to? The 0 vector, exactly. So you can imagine taking this expression, let me put a box around it. You can imagine taking this expression and setting the whole thing equal to the 0 vector, right? But of course, this boxed expression is really just this, after I multiply it back together, instead, after I unbust the variables. If I kind of go in reverse, take this boxed equation, before I busted out the variables, it was just equal to this, right? Now imagine setting this equal to the 0 vector now, right? What would you conclude about if you match these slots up, what are you going to conclude about the Q, the R, the S, and the T?
They're all 0.
They're all 0. So what does that tell you? Oh, I had a linear combination of my vectors. I canceled it out to 0, and I proved that the only way to make that linear combination cancel out is to cheat and make every single constant equal to 0, right? You match this up, T has to be 0, S has to be 0, R has to be 0, and Q has to be 0. So the answer to this question is yes. And you can do the Li test just as I explained. Everybody okay with that?
Would you also know by having only one qubit?
Yes. Oh, I'm so glad to hear you do that, because that was the very next thing I was going to say is we didn't need to do all of this work because of what Christian's heading towards. Christian remembers that we have this theorem, and in this problem, n, which is the number of columns of the matrix, is 5. And Christian can tell, just from the row echelon form, that the rank of the matrix is 1. There's only one pivot here, right? So the rank is 1. So the nullity, therefore, has to be what? 4. Okay, that means we know the dimension of the null space in advance. We know that it's 4. I shouldn't say in advance, but we know that the dimension is 4. Right? Oh, this is awesome. We know that the dimension of the null space is 4. How many vectors do I have in this spanning set? 4. Remember that if I give you the right number of vectors, then they're either both or neither. Well, we already know that they're a spanning set. So then they have to be Li also. Isn't that clever? We don't have to do this brute force Li check here, where we take this linear combination, set it equal to 0, and solve for the constants. We actually don't have to do that. We can use a more sophisticated approach, which is to simply say that we know that the dimension of the null space is 4, and we have 4 vectors right here. So they are either both or neither. And because they already are a spanning set, that's how we came up with them, it must be that they are both. It's kind of nice. As soon as they are one, then they have to also be the other. So, oh, that's really good. So you could justify this one, and this would be a great test question because you could do it 2 ways. You could either go ahead and check linear independence in the traditional way using the 4.5 material, section 4.5, where we have the definition of linear independence. You can do it that way. Or you can do it a little bit speedier way, which is to take advantage of the fact that you know the dimension of the null space is 4. Isn't that nice? Okay, so that's great. Any other questions about this example? Okay, let's go on to another problem then. Start over on something new. Oh, I had one other thing I was going to say. Of course I just erased it. I could also have asked you about the row space or the column space of the matrix. So, just really quickly. This was the matrix A again. Just remind me one more time, just want to make sure everybody knows this. If I ask you for a basis for the row space of this matrix, what would you do?
The row of matrix A.
This one?
Yeah, no, the A
Yeah.
would be the top row because that's
Why?
your pivot. Your pivot's in that row.
Okay, so you do the row echelon form again, right? And then the pivoted rows become your basis for the row space. You actually don't have to go back to the original matrix. You can just take this row right here.
Yeah, that was for call space. You go back to the
Right.
original matrix.
And that would be the other question, like what is a basis for the column space? By the way, now you can kind of see why you have to go back to the original matrix. Imagine you took just the pivoted column for the column space. You would get the vector 1, 0, right? But if you look up here, there is no column that is basically a multiple of 1, 0, right? Every single one of these columns, just look at these 5 columns. Every single one of those 5 columns is a multiple of that column, right? So your basis for the column space, if I asked you for a basis for the column space, I would not want to give the answer as being 1, 0. I would want to give the answer as being 1, -4. That would be a better answer. That would be a correct answer. Okay, and it's one-dimensional. It's just one dimension. All columns are just multiples of the first column in that matrix. Okay, great. So row space, null space, column space, rank nullity theorem, that's kind of what we're looking at on a question like this. Okay? Super. Okay, so let's try another example. Okay, so here's another problem. Number 2. Let S be the set two plus x cubed, 1, 2x squared plus x cubed, and 1 minus x squared. Let's take that set. I'm changing the problem from what's on the handout there. Okay, and then the question is, and then let's let V be equal to P3 of R. And I'm just simply going to ask, basically, is S Li a spanning set, both, or neither? Okay, so we're going to just throw that up there. Okay, so there's no matrix. These are polynomials this time. But how do I approach this problem?
Well, it has 4 vectors.
I have 4 vectors. What is the dimension of V? N plus 1, which would be 4. Okay, so it's 4-dimensional, and I have 4 vectors. So I gave you the right number of vectors, yeah? Does it mean it's a basis? It's either both or neither. Okay, so guys, whenever you have one of these 4-choice problems, you can always cross off 2 of them right away by just counting how many vectors you have. Okay, so it's either both or neither. How am I going to decide whether it's both or neither? Ali?
I had a question.
Oh, question.
Can you repeat what you said about crossing the 2 out?
Well, if I give you the right number of vectors, in this case I gave you 4 vectors in a 4-dimensional space. If I give you the right number of vectors, then your vectors will either have both of these properties or neither of these properties. So I know that I'm not going to be circling these 2 answers. I'm going to either circle both or neither. On the other hand, if I gave you too many vectors, then you would be crossing off Li and both right away, because you would know that it can't be Li. And if I gave you not enough vectors, then you would be crossing off spanning and both right away, because I would know that I couldn't span the space with those vectors, and I would just have to test for the linear independence. Okay, so that's what I was basically referring to. Okay, so what do I do to answer a question like this? Yeah, I need to make a matrix out of these vectors, and how do I make my matrix? How do the vectors go into the matrix? Not busting out the variables right now. First of all, there are no variables up there. The x is not really a variable that we can bust out.
Each vector would be a column.
Right, each vector goes into the columns of a matrix. So it's just, so we're going to form the following matrix. Basically, the first vector goes into the first column. Now, how you put it in the column is kind of up to you. Let's say I'm going to put the constant terms first, and then the x terms, where there is no x term, and then the x squared term, which there is no x squared term, and then the x cubed term, which has a 1 on it. Right? So those are just the coefficients. So that would be my first column. My second column would look like what? 1 and then a bunch of zeros, exactly. Okay. My third column would look like 0, 0, 2, and 1, right? And my fourth column would look like 1, -1, -1, and 0, right? Okay. So we can form this matrix, and we can augment this matrix with either the 0 vector or a arbitrary polynomial coefficients vector, depending on whether we're thinking about the span question or the Li question. Okay. So far, are we so good on that? Now we have a 4x4 matrix. So the thing is that when I give you the right number of vectors, they will always form a square matrix. So I don't actually have to do EROs here if I don't want to. What could I choose to do instead? Right, I can find the determinant of this matrix and then use that to decide whether it is or isn't a vector space. So, or whether it is or isn't invertible. So let's do the determinant of the matrix. Okay? Actually, we may need to practice this again. I mean, even though the determinant was really in chapter 3. Remember what I said the first day of the semester? This class just keeps building on itself. We keep having to use the material that you learned before. So if I had to find this determinant, how would you suggest that I would do it?
Cofactor to that column 2.
Right. The second column is the best choice because there's only one number that you have to work with. So I'm going to expand column 2. span column 2. So when I do that, don't forget there's that plus minus pattern that we have to keep track of. So this is a minus entry. So it's going to be minus, you get minus the determinant of the 3 by 3 matrix that you get by crossing off that row and column. So that leaves me with this 3 by 3. You have 0, 0, 1 there, and then 0, 2, and 1, and then negative 1, and negative 1, and 0. And all I need to know is, I don't even need to know what the number is, I just need to make sure it's not 0. And you can probably tell already that that's not 0. Okay, that determinant is not 0. Yeah, come on.
Why did you cross out that first one?
Say, oh, because I was cofactor expanding the second column, and I was looking at this entry right here. And when you're finding the cofactor for that entry, you have to cross off the row and column that that entry are part of, and look at the submatrix, the 3 by, in this case, the 3 by 3 submatrix that you get after you cross that off. So I crossed off that row and column, and I took the 3 by 3 matrix that was left, and I put it over here.
Okay.
And the minus sign is just because we're in an odd position in the matrix. Yeah, there's something?
When I looked at the set S, in each of the cases there is a different exponent in all 4 of the cases. So from just seeing that, you already know, like, there's no way to make
Okay.
to make a linear combination.
Okay, let me come back to that point in a second.
Okay.
Okay. Not quite that simple.
No. Okay.
No. But here certainly, does everybody agree I got a non-zero determinant, therefore I can say it's both. Right? I can say that it's both. If I had given you this set, this is just another little follow-up observation. If I had given you this set, notice that each of my 4 polynomials has a different degree. This one is x cubed, this one is x squared, this one is just x, and this one is a constant. I can tell that, for example, there's no way to write this third vector using the first 2, because I can't get an x squared out of the first 2, right? If I try to write a linear combination of the first 2, I'll never be able to get an x squared to show up. So this one is a new vector that's outside of the span of the first 2. Similarly, the last vector is not expressible in terms of the first 3. So if you're thinking about linear dependencies, right? Linear dependencies are where one or more of your vectors can be written in terms of the others. You wouldn't be able to do that here. You definitely can't write this one using these 3. You can't write this one using these 2, and so on. Okay, so there's no dependencies there, and if you want, you can obviously build a matrix and confirm for yourself. This one's easy because this one turns out to be upper triangular, so the determinant is just the product of the diagonal numbers. A non-zero determinant is what you're going to get here, right? This one I don't think is so clear because I have 2 different x cubed polynomials. I have 2 different polynomials that have x cubed in them, so I might be able to cancel them out somehow.
But I was thinking because on the second one, there's an x squared that none of the...
But there's an x squared over here, so then now I can start using this one to like cancel out the other one. You know, it's not as obvious. I can't just kind of look at it and say, oh, there's no way to get them to cancel out. Because I could conceive of these 2 canceling out with the x cubed parts, and then these 2 canceling out with the x squared parts. I mean, actually, if anything, you could look at the x coefficient and say there's only an x here. None of the other 3 polynomials have an x in them, which means this polynomial cannot. If there was a linear combination of these that canceled out, this polynomial would have to have a 0 in front of it. And as soon as that has a 0 in front of it, now you're going to have trouble getting the x squared parts to cancel. I could do an analysis. I'm not saying it's impossible to reason it through that way, but it would not be totally straightforward. I would be much happier doing it as a matrix myself. Okay, everybody good with that? Okay, super. Let me do one more of those because that one comes out so easy because it's a square matrix. Let's take one that's not